Thanks for being here today. In this presentation, we'll take a look at how to do PCB layout electrical sign-off with automated rule checks and hyperlinks. I want to start by introducing the hyperlinks products family, and next I'll be highlighting verification challenges and what a tough job it is to do an electrical sign-off of a printed circuit board. And then I'll talk about traditional design process and a modern sign-off process. A better approach may make sense with the modern complexity of PCBs. Next, we can introduce electrical performance, sign-off, and automation in this process. This leads to design rule checks with a built-in electrical perspective and automating the tedious things to inspect for on a PCB. As you may know, Hyperlinks is a family of products that includes Hyperlinks Schematic Analysis, Hyperlinks AMS, Hyperlinks DRC, Hyperlinks Advanced Solvers, and Hyperlinks SIPI. Hyperlinks Schematic Analysis does automated verification of a PCB schematic. You can find and resolve errors in your schematic before you start simulating, ensuring that the time spent modeling and simulating is time well spent. You can use Hyperlinks AMS to address general purpose analog, power, and mixed signal design challenges. Hyperlinks DRC, which provides fast electrical rule-based design checking of PCB layouts. Hyperlinks DRC can identify layout issues in a fraction of the time that simulation requires. And screening designs with Hyperlinks DRC before investing in detailed modeling and simulation will help speed up your design cycle. Hyperlinks SI and PI, which share a common user interface. Hyperlinks SI performs signal integrity analysis of DDR interfaces, SerDes-based serial channels, and general-purpose high-speed design. Hyperlinks PI performs DC and AC analysis of PCB power delivery networks, or PDNs. Hyperlinks Advanced Solvers, which provides accurate 3D electromagnetic modeling of PCB structures, and are seamlessly integrated with Hyperlinks SI and PI to provide complete front-to-back analysis flows. So as you can see, Hyperlinks is an integrated family of products for high-speed system design, automated optimization, and verification. By design, we mean all the planning and analysis that you do before a layout to define the rules you want to use to place and route the board. By optimization, we mean using automated tools to improve design performance for a metric of interest. You can certainly use an interactive design capture, analyze, or view loop to improve your design. That takes too long. We'll look at how hyperlinks can help you improve design performance automatically. By verification, we mean post-layout analysis, or what you do once the board is routed to determine that the design is ready to release to fabrication. There are two main design application areas for hyperlinks. They are serial link and DDR interface design and verification. Hyperlinks also encompasses general purpose signal and power integrity. Hyperlinks is tightly integrated with Siemens family of PCB design capture and layout tools. Design is an iterative process as you lay out a board. Using analysis during the physical design cycle can help you tune and improve the design in real time, rather than waiting until layout is complete when it's too late to make substantial changes. Combining hyperlinks with Siemens design capture and layout can significantly reduce your design cycle and improve your design's performance. Although hyperlinks can analyze any board layout from any layout tool, it's better with Expedition and or the Siemens Enterprise Data Management tool. You can access any hyperlinks tool from Expedition Layout by exporting a current copy of your board and directly opening it with Hyperlinks SIPI, Hyperlinks DRC, or Hyperlinks Advanced Solvers. Another method of integration of using hyperlinks with Expedition Layout is through the Analysis Control Client, or the XAC. This is an embedded Expedition GUI panel that allows you to run Hyperlinks DRC, Hyperlinks Power Integrity DC Drop feature, or the FastRD solver from Hyperlinks Advanced Solvers. These three features are available, and you can run them and make real-time changes to the board because you're still in the Expedition layout environment. Hazards or rule violations from Hyperlinks DRC will be reported with Hazard Explorer, allowing layout experts to run rule verification directly in their own tool. Beyond Expedition, all the PCB tools are managed by Enterprise Data Management Ecosystem. Hyperlinks is tightly integrated with EDM design, and that reason is based on our digital transformation initiatives. Now I'd like to shift focus to talk about verification challenges. When designing for signal and power integrity, there are many obstacles for an engineer to overcome. First off, there are a constantly evolving set of standards and protocols. Each comes with an extensive mind-numbing documentation to ensure proper operation under all conditions. Keeping up with the constraints and ensuring adherence during design poses a significant challenge. Second, most engineers leave school with only the fundamentals regarding signal integrity, so they have to teach themselves or rely on a limited pool of domain experts, often outside of their organization. And associated with this, there's a lack of expertise regarding electromagnetic theory and associated modeling to simulate effects on a design. This leaves an engineer unsure of what's most important in the design, and then a decision has to be made on what to model because you can't model everything. It would take too long and it would be too costly. You also have to prioritize what electrical sign-off strategies you will use before going to manufacturing, and most often than not, you won't have time to check everything before tape out. And while product and design complexity increases, it should be no surprise that associated tool and process complexity also tends to increase. Let's look at some impediments to utilizing an efficient verification strategy. First off, tool complexity and usability typically scales with the complexity of the models you'll need to validate for your design. Models come in all forms, from simple datasheet descriptions up to complex S parameters or 3D mesh structures. Associated tool complexity is measured in terms of the key steps to validation, setup, actual analysis or verification, and review of the results. Ideally, tool complexity would maintain a high ease of use regardless of the modeling complexity. The tools used for validation are often uniquely focused on one problem and not integrated, meaning that users have to learn multiple tools and often stitch the results together by hand. And finally, due to the tool complexity and inherent complexity of the problem to be solved, specialists are often used for validation. The problem is that these bright folks are spread thin within engineering organizations, resulting in bottlenecks and incomplete electronic system validation. Now let's look at the design process. A conventional PCB design process is fairly linear with a schematic creation and review, layout review, and then manufacturing review. Usually, electrical verification and final sign-off is left for the prototype lab at the end. Aside from the obvious cost and time wasted at this late stage, there's also no way to do a root cause analysis on why that problem was created or look at the options to resolve it. One step better than this is validation right before the prototype. This is where most analysis tools get their start because someone's trying to catch a problem they've been having in prototype or in full production. This approach is the one noted earlier with the specialist, the complex tools that are pieced together, different vendors, and those fun bottlenecks. I want to suggest a better approach and use automation to improve this new approach. We call the ideal process the shift left approach because validation is pushed as early as possible in the process. Ideally, right after an error could be made in the system definition, the schematic, or the layout stages, and the person running the validation is the author at that stage. For instance, the design engineer, the schematic stage, or the layout designer at the layout stage. And to enable this process, the validation tools must be tightly integrated with the authoring environment and easy to use. Ideally, the digital twin model of the design is automatically created, greatly simplifying the validation process. By the way, this approach shouldn't threaten the specialist deployed at the end of the design process. By enabling the design authors to do the validation, the specialists are freed up to perform more complex, complete multi-physics analysis on only the toughest problems, and not the whole design. This approach also should not threaten design authors who see it as adding extra steps and tools into their workflow, because the net result is a shortened design cycle with fewer respin interrupts and higher product quality. And also by automating the tedious, we can make these left shift approaches in the stage reviews really quick and easy to perform and not costly time added to their day. The focus of today is automating the layout review stage, and we'll do so with electrical rule checks and hyperlinks DRC. I want to introduce the idea of progressive verification. Automate the tedious, run hyperlinks DRC first. In our methodology, we start by running electrical design rule checks during layout to look for common problems. This is where we will be spending time in our lab and learning this stage of electrical verification. The other stages included in a traditional PCB design flow would be to use the knowledge we gained from Hyperlink's DRC to dive deeper into the standards compliance analysis to make sure we're following the protocol requirements, whether it's SerDes or DDR or whatever interface we're putting on our PCB. Finally, once we've gotten as many problems off the table as possible, we'll introduce models, IBIS AMI models, or vendor-based model simulation to predict how the system will perform with actual devices and settings. Feel free to check out our other workshops that dive deeper into these two areas. We call this whole flow and methodology progressive verification, and it allows us to find layout problems as early in the design cycle as possible with as little effort as possible. We deliberately separate verification into different stages so that we can defer time-consuming and expertise-intensive analysis, allowing us to make the best use of our scarce SI expert. We start with simple analysis and then add accuracy in controlled stages because the time needed to model and analyze the system increases as we make the analysis more accurate. And that's true with any tool, not just with hyperlinks. The time and expertise needed to perform simulation increases dramatically as analysis accuracy goes up. Let's take a deeper look at the first stage of progressive verification, the electrical rule sign-off stage. Validation of the electrical performance of a layout is another task that's often done through visual inspection. This time scanning through multiple layers for ground return paths, potential noise sources, and many other problems. Critical issues impacting EMI, signal and power integrity can be quickly identified. The rule checks can also be used to screen the full board for problems that require further analysis using simulation. The rule checker has an intuitive, easy-to-use environment that includes a wizard for setup and errors found and can be quickly reviewed. An extensive set of built-in rule checks is included, but additional custom rule sets can be added. And again, we've integrated this checking within the Expedition environment so that electrical rule checks can be run concurrently as the layout proceeds and not just at the end. Hyperlink's DRC encompasses all of what is needed for the automated rule checking process. There are built-in checks around high voltage safety, IC packaging, EMI, signal integrity, and power integrity. There's a script writing debugging environment, so you can write your own rules in the tool, as well as services for us to write custom rules for you. The rules have default parameters that can be easily adjusted depending upon your PCB. Some examples of EMI rules that come out of the box are traces crossing splits, reference plane change, via stub length, and nets near plane edge. Some signal integrity examples include impedance checks for single-ended or differential pairs, numbers of vias, and termination checks, as well as topology checks for DDR. Some out-of-the-box power integrity rules are focused around decoupling capacitor proximity and power net width. Remember hyperlinks? DRC has an electrical perspective built into the rules that goes beyond what the layout DRCs can only check for, which is spacing and distance. The decoupling capacitor rule checks if it's near enough to an IC power pin to properly decouple it, but also checks the capacitance to see if it's the appropriate value to be able to decouple it properly. High voltage safety has a built-in creepage analysis engine, which makes the extremely tedious process of manually calculating and inspecting for creepage voltage to affect nearby components on the board, making that an automated process with Hyperlink's DRC. Some rules can incorporate IBIS models. In previous slides, I've discussed the challenges of manual inspection, and here I summarize the benefit of using the automated checks. It depends on the rules, but usually the automated checking takes seconds to minutes by anyone. Your board is checked against the rules, and the violation report will be generated. It's very easy to compare between before and after, which helps you to accumulate knowledge. The great benefit of these rules is their background and explanation of how the rule is written and what it checks for. So, if you're not familiar with some signal integrity or power integrity concepts, you actually can learn from the tool and apply them on your layout. Another really important benefit of the automated checking from Hyperlink's DRC is that anyone can check at any time. Because you don't need to be an expert to run the rules, and they run so quickly, we can have the layout designers run them while making the layout. This frees up a lot of back and forth between the SI and PI expert and the hardware team, where they can catch quick problems often and easy. And if there's something that needs a deeper dive, then they can call the expert and use Hyperlink's SIPI or Hyperlink's advanced solvers. But a lot of these checks don't require that deeper of a dive. Also, because the process is captured and preserved with the rules, you can deploy these rules and parameters to future versions of the board, or in the cases where you copy and paste PCB, manage blocks, and circuitry to future designs, bring the rules with you and capture the electrical verification process so that you can easily repeat it for future work. Say you hire a new user. You can share the rules set up with them that's targeted to the board. Have them run the rules immediately versus trying to teach somebody about deep theory and what to check for. And as you get started teaching them about signal integrity and power integrity, you can use the rule deck to be your starting point. We've automated a lot of that for new users to get up and running quickly. And the last thing is that Hyperlink's DRC does not make mistakes because it's based around automation. Sure, parameters for checks can be entered wrong by the user, but the point I'm trying to make is that the rules scan the board. They will not get tired. They will not need to take a coffee break. And they will not get interrupted by meetings or other work, as we all do. Human error is an element here. When you manually check for a board during this process, layer by layer, net by net, it's virtually impossible to do so without making a mistake or without having time to check everything. So let Hyperlink's DRC do the tedious scanning and allow you to scan more nets. Oftentimes, we only had time to check certain specific groups of nets. Let Hyperlink's DRC check them all in a matter of minutes. Let's take a look at how Hyperlink's DRC can capture a process and organize it for a user group. To use the rules to check, here's the customized HLD set file for Hyperlink's DRC. We call it a handy HLD set. My colleague Bill created this setup for his customers. Rule groups can be organized by type, such as EMI, SI, or PI. They can also be set up by technology, like SerDes protocols or DDR topologies. The user has full autonomy here on how they name and organize their rule group. You can copy and paste common rules that have parameters that will change for or vary depending upon the nets. For instance, you will want differential impedance checks, but the targeted differential impedance will change from DDR2 to DDR3 to DDR4 and 5. Same goes for other protocols. Just follow the design rule guidelines for whatever structures are on your board and use the out-of-the-box rules to target them. Some rules will run on the entire design, and some will only run on a certain area. The rule groups can focus the rule scope or use object lists to target specific groups. As I mentioned, electrical rule checks automate manual inspection, finding problems in seconds or minutes that would take hours or days to find using modeling and simulation. These checks cover a wide variety of power and signal integrity issues. Traces crossing gaps and planes are a good example of problems that can be found quickly. A DRC analysis can process hundreds of signals per second, identifying exactly which signals have problems and where. Finding a trace crossing a split using a simulation is problematic. Modeling and simulation are time consuming. The actual effect on signal quality may be relatively small, and isolating the exact location of the problem from simulation results can be difficult. Hyperlink's DRC performs analog, EMI, PI, SI, and electrical safety checks in a fraction of the time it takes to perform those same checks manually, producing detailed reports that show exactly where and how each violation occurred. It also produces reports that can be given to PCB designers to quickly locate and correct each problem when using the Siemens Flow. They're fully embedded in our layout tool and managed by Enterprise Data Management Process. Hyperlinks workshops get you up and running quickly by documenting complete workflows with detailed step-by-step instructions and videos. Hyperlinks workshops such as this one can guide you through the process with working examples so you can hit the ground running on your own design simulations. Hyperlinks workshops can be downloaded from the Support Center by following the Learn and Explore link from Hyperlinks area and selecting workshops. You can see a list of the different workshops on the right of the screen. Thank you for your time today. And remember, automated electrical rule checking and layout verification is easier with hyperlinks.